This is the review for the Physics 221 final exam, and I'm going to go through the topics that we discussed so that you can choose where to focus your attention on thinking about what to study for and what to have looked over most recently. We started the semester looking at Ohm's law, that's V equals I times R, and we applied that to looking at the voltage and the current passing through resistors, as well as the equivalent resistance when we had series and parallel resistor circuits. We started out just with pure series and pure parallel resistor circuits, and we later moved on to combined parallel series circuits. Also switches. What is a switch? It basically looks like this. The schematic looks something like this, and it closes and causes a circuit to complete. And we use them throughout the labs this semester, and it's important that you know what they do and that they turn on and off. How do you measure current? How do you measure voltage? We used an ammeter to do that, to measure current. And you always had to break the circuit, if you remember, to measure current. And to measure voltage, we used a voltmeter, and we put the voltmeter across whatever circuit element whose voltage we wanted to measure. It could be a battery, it could be a resistor, it could be a light bulb. We also discussed power dissipation. That you can calculate that by multiplying the voltage and the current. You're going to actually get units of watts, which is the same unit we talked about in first semester physics. And power is dissipated by a resistor. That means it's converted from electrical energy to heat energy, or in the case of a light bulb, from electrical energy to light energy and heat energy. And that power is supplied by the battery. And so the current drawn by the battery, the more the current for a 12-volt battery, for instance, the greater the power draw is going to be on that battery. And we also talked about solar cells, and those are another source of energy, and we talked a little bit about how they worked, just a tiny bit about the physics behind them. But we looked at the IV curves of batteries and solar cells, and solar cells tend to want to provide constant current until the resistance is so big that they can't provide that current, and then the current drops off. Batteries, on the other hand, want to supply constant voltage, and they do that until the resistance gets so small that that voltage can't, that the current gets so big that they can't supply that same voltage. So that was a distinction between how solar cells work versus how batteries work. And then we also discussed energy and how it relates to power. This is similar to first semester physics. Energy is measured in joules, calories also, but we looked at it in joules. And power is the rate at which energy is transferred, dissipated, or provided to a circuit, and that's joules per second, or watts, as we talked about. We mentioned how a solar cell works. The concepts of efficiency are important. When something's more efficient, you're getting more out for what you put in. I just saw an article today on solar cells. When they get hot, they become less efficient. And so there's some new technologies that are pulling water out of air on hot days and then allowing the water to evaporate. And that's cooling the solar cells down and increasing their efficiency by a significant amount. And then when we talked about a photovoltaic system where you have a solar cell, it charges a battery, and that battery can provide energy to a load. And those loads are switched on and off. And then you have a charge controller that determines when the battery needs to be charged. And so it kind of provides the brains behind the whole system. But that's the basic idea behind a photovoltaic system, and kind of like the one you built in lab, actually exactly like the one you built in lab. We talked a little bit numerically about how large a battery would you need depending on how many light bulbs you're hoping to supply during the day. That relates power and energy. If you have a lot of high-powered light bulbs that you want to have on for a long period of time, you're going to need a bigger battery to store all that energy during the day or during the night so that it doesn't run out. And then you're going to need more solar panels to fill the battery back up during the day. So it's like a budget. It's kind of like doing your bank account budget, making sure you don't spend more than you have. You can't in energy. You have to, once you're out of energy, there's nothing more to spend. So it's kind of like a bank account, except I guess you can go into debt and use credit. You can't quite do that the same way with energy. How to draw circuits, making sure you know the circuit diagrams, what they mean. You won't be drawing them because it'll be multiple choice, but you'll have to pick which circuit diagrams represent certain circuits. And how to connect circuits on a circuit board. We did do problems like that on different exams earlier in homeworks where you're figuring out which holes you could put resistors in or whatever circuit components in order to make the circuit be the one you want it to be. Then we started talking about charges. You have positive charges and you have negative charges. There are no neutral charges. Neutral means that you have positive and negative that combine and they cancel each other out. So everything is positive and negative. There's just two types of charges. What charges attract or repel each other? Opposites attract, likes repel. And so that helps us to determine what is I hat, what is J hat when you have a few charges sitting in a region. And what's the difference between insulators and conductors? If you have charge on an insulator, it's just going to sit there unless you spread it around. But on a conductor, the charge is going to try to spread out as much as it can. And that leads to different characteristics for how insulators and conductors work with charges. They have a profound effect when they're on conductors in that they spread themselves around, and they don't do that on insulators. So we had some labs and activities that show how that can affect things. You can actually get charging by induction on conductors where you have the charges that move to one side of the conductor and the other ones stay there. And so you get this big charge separation that allows you to charge a conductor using the technique of charging by induction. There's, of course, charging by conduction, where you simply touch two objects together, and the charge on one will move to spread itself out on the other one, assuming they're both conductors. They'll spread. And I actually already mentioned resistor circuits, so I'm repeating myself here, but knowing what current is, it's the flow of charge. Once we talked about charge, hopefully you had a better understanding of current. Already talked about that. Then we talked about Coulomb's law, and that tells you what the force is going to be between two charges. It's F equals K times Q1 times Q2 divided by R squared. We spent quite a bit of time working with that and noting the direction of the forces that charges experience as a result of other charges. Not only did we talk about the forces between two charges, but we talked about something called the electric field, which represents the region of space that a charge would experience a force if another charge were there. So a single charge creates an electric field that other charges experience when they're there, and then they'll get that Coulomb's law of force associated with them. But if you don't have a second charge there, the first charge creates an electric field that tells you what a second charge would experience if it were there, in terms of what force it would experience if it were there. And so for a single charge, the electric field looks a lot like Coulomb's law, but there's only one charge in the equation, just K times Q divided by R squared. So that's when you have a single charge, it creates an electric field. Of course, if you have a line of charge, you create an electric field. And if you have a plane of charge, you create an electric field. We didn't talk so much about the line of charge, but it will also create an electric field. But in a plane of charge, it creates an electric field. And of course, the electric field doesn't vary with distance away from the plane if it's an infinite plane. And we saw actually a lab that looked at that, but using light rather than electric field. But you saw the same idea. When you're really close to a computer screen, it doesn't matter if you're a millimeter away or 5 millimeters away. It's going to be just as bright. That's what we saw. Same idea with infinite plane of electric field. And in addition to the electric field, we talked about the potential, which is volts. That's the same volts that you saw in circuits. And the potential is associated with how difficult it is to get it. You can think of it, how hard is it to get a charge close to a certain amount of a certain another charge. The potential gets higher. It's kind of like climbing a mountain. If there's a positive charge here and I want to bring another positive charge there, it's really hard to bring it there. It literally is like climbing a mountain, and the closer you get, the steeper it gets. And if it's negative charges, it's kind of the same way. If they're really close, there's a lot of potential there. And so anyway, that's something we talked about. And the equation for potential gives you also volts. It's K times Q divided by R for a single point charge. That's the potential associated with a single point charge. Far away from it, whether it's positive or negative point charge, it's going to be zero potential if that's the only charge in the universe. Close to it, if it's a positive charge, it's going to be really big. Close to it, if it's a negative charge, it's going to go really negative. Big but negative. And potential is not vector, but electric field is. So with electric field, you had to put an I hat and a J hat in there. With potential, it's just a value. It could be negative, could be positive, but there's no direction associated with potential. And as I was spending most of my time talking about point charges right there, but you have the same thing with planes of charge. And we had some problems where we're looking at potentials associated with planes of charge. What's the potential as you get further and further from the plane of charge? Since the electric field is assumed constant for a plane of charge, or between two planes of charge, which is a parallel plate capacitor, the potential goes from maximum on one to, we can assume, to be 0 on the other one, and it varies linearly between them. And we spent some time talking about that. You can review those notes and ask me if you have other questions on it. Again, put two planes of charge, opposite charge near each other, you have a parallel plate capacitor. We talked about how to calculate that capacitance. It's the area times epsilon 0, which is the permittivity of free space, divided by the space between that, the spacing between them. We did a lab on that too that you might remember. And if you add something in between those two plates, you can actually cause the capacitance to increase. That material is called a dielectric. And we talked about why that's the case, because the molecules in there realign themselves and allow more charge to accumulate on each of the plates. And that gave us a relationship between the charge on the parallel plate capacitor, the potential across the parallel plate capacitor, and the voltage across the parallel plate capacitor. Q is equal to CV. That's the Chula Vista equation that I use quite a bit. And then the electric field between capacitor plates. When you have a single plate, it's the charge density divided by 2 epsilon 0. But when you have two plates of opposite sign together, it is the charge density, which is the amount of charge per square meter on each plate, divided by epsilon 0. The factor of 2 goes away because in between them, the electric field is reinforced from each of them. So it's twice as big when you have two plates of opposite sign than if you have one plate of just one sign of charge. You have the same amount of charge on this plate here. The electric field between them, if you remember, is going to be double what it was with just a single plate. Makes sense. But outside of the area between the two plates, the electric field is 0. We talked about series and parallel capacitors, just like we did for resistors. Came up with some equations that address series, parallel, and combinations of series and parallel capacitors. We worked with RC circuits. What is R times C? Well, it's the time constant of the RC circuit. The bigger that number, the longer it takes charge to discharge out of the capacitor through the resistor. And we did a lab on that. It's worth noting that. There will be certainly a question on RC circuits. Then we talked about magnetism. Magnets, north and south poles, are not electric charges. Sometimes they're confused for them. They're not. They have some similarities and they're related, but they're not the same thing. Magnets will not attract an electric charge. But magnets will attract moving charges if they're moving in the right directions. And what creates a magnetic field? It's kind of this interesting circular relationship where if you have a moving charge or current in a wire, you're actually creating a magnetic field that goes around the charge like that. And the magnetic field is direction. It's a vector. And it circles the moving charge. It's not a stationary charge. If it's a moving charge, a wire, the magnetic field will circle the wire, kind of like a cylinder around the wire. And the direction of the magnetic field can be determined by using the right-hand rule. Putting your thumb in the direction of the current, fingers wrap in the direction of the magnetic field for your right hand. You can also create a solenoid, which is if you coil the wires together, you get the magnetic field really strong through the solenoid in the direction of the solenoid. And again, you can use the right-hand rule to determine if the magnetic field is directed that way or that way. You wrap your fingers in the direction the current's flowing, thumb points in the direction of the magnetic field for the right hand. We talked about the magnetic field associated with a single wire, since it creates a magnetic field, and with a solenoid. We did a lab on the solenoid, the strength of the solenoid. And distance from a wire, it's mu0, which is the permeability of free space, 4 pi times 10 to the minus 7th. Multiply that times the current passing through the wire, divide it by 2 pi r, and that gives you the strength of the magnetic field at some distance away from the wire. Now within the solenoid, it's the number of coils per meter that make the magnetic field stronger. The more coils you have per meter, the stronger the magnetic field. Multiply that times the current times, again, the permeability of free space, and you get the magnetic field strength within the solenoid. We use the right-hand rule to discuss the direction a magnetic field will have on the motion of a charged particle. Charged particle has to be perpendicular, has to have a component of its motion perpendicular to the magnetic field in order for it to experience a force. So when we use the right-hand rule, we did a lot of examples of that, there's quizzes on it. Check that. If you have questions, you can ask me. But as a result of that force that a moving charge experiences in a magnetic field, it experiences a force that causes its motion to change. If you actually plot the trajectory of that charge, it's going to follow a circular path within a uniform magnetic field. And the radius of that circular path is a function both of the mass of the charged particle, the size of the charge itself, the strength of the magnetic field, and the velocity in which the charge is entering the magnetic field. And we came up with an equation that relates all of those. Then as we started rounding out the end of the semester, we talked about how currents can be generated from magnetic field. So let me make sure that you're clear on this. Currents create magnetic fields. When magnetic fields change and they're near conductors, those in turn create currents. So there's a cyclical relationship going on here. Lenz's law was what allows us to determine how those currents are generated from a magnetic field. Lenz's law says those currents are generated such that they're going to create a magnetic field of their own that's going to oppose whatever magnetic field is changing. So they're going to try to make that change stop. And we gave a number of examples of that and how that works. We also talked about magnetic flux. That is the product of magnetic field and area over which something exists. And if you have a coil, the flux is N times the magnetic field times the area. And the magnetic field has to be perpendicular to the area. And if the area is like this, so that it's in line with the magnetic field, like this, then the flux is going to be zero. So if you have a rotating coil here, you're going to have a changing flux. And that changing flux leads to sinusoidal voltages and currents, which is how we get AC currents. And then, of course, Faraday's law tells us what the voltage is going to be as a result of a changing flux through a coil. You take the first derivative of the change of the flux and how it changes as a function of time, and there's a negative sign in there. That gives you the voltage. And we did a homework example of that, and so you saw that on, I think I did a lecture example, and there's a homework problem about it. And you can apply that to both the generator, which is how that's how we create the currents and voltages that we use in our homes and everywhere these days, is really primarily as a result of the changing flux passing through a coil, or that a coil passes through, or a coil spinning, and the flux that causes a change in flux that the coil experiences, and it creates the voltages that we experience. And the same principle, Faraday's law, also applies to a transformer. That's what allows us to change AC voltages, to step up and step down, and to change AC currents, to step those down and step those up, in contrast to the voltage. If the voltage steps down, the current steps up. So we talked about that as well, really useful applications of Faraday's law. Finally, we talked about optics. And I did some demonstrations and some lectures on a bunch of topics, but these are the only things that you can potentially expect to appear on the final. The law of reflection, that says the angle of incidence. And remember, the angle of incidence is the angle that the light is approaching a mirror or a lens. That is going to be measured from the normal to the mirror or lens. That's just how that angle is measured. For a mirror, the angle of incidence equals the angle of reflection. So, and we had a lab on that. We saw a lot of light rays and things like that bouncing off a mirror. And so it's a very straightforward calculation. And there's some really neat demos you could do with mirrors on that. Probably have to do this in a future class, but mirrors are pretty interesting. They're simple in a way because that angle is the same. Angle of reflection is equal to the angle of incidence. Now, Snell's law tells you what happens to the ray that passes through from one type of medium to another. And that's the law of refraction, where you have n1 sine theta 1 equals n2 sine theta 2. And that's what causes different dispersion, because different light has a different n for a different type of medium. That's what allows us to get rainbows and things like that to appear from the sky, the rainbows we see in the sky, and also from a prism, because different wavelengths of light have a slightly different n. But really, for this class, you just can assume that the n is going to be constant for, I'm not going to talk about different wavelengths of light, how they refract slightly differently. All you really need to remember is that n1 sine theta 1 equals n2 sine theta 2, so light bends when it enters a medium of a different index of refraction. And I might ask you how much it bends. And again, the bend is measured from the normal to the interface. And finally, the lens equation, that's the last thing I might ask you about, tells you the relationship between the focal length and the object distance and the image distance. And also you could figure out what the object size is, what the image size is if you know the object size. And the lens equation is 1 over the f, which is the focal length, equals 1 over the object distance plus 1 over the image distance. And there's some examples of that calculation in the lab and in the bonus homework. All right, if you have other questions, you can feel free to email me. Good luck as you round out the semester. It's been fun having you despite the challenge of COVID-19 and what it's forced us to do. But I'm hoping that you got something out of this class that you can take with you. Take care.